All right, let's jump right into it. Today, we're tackling one of calculus's most powerful tools, integration by parts. And we're not going to just talk theory, we're going to get our hands dirty working through exercise 8F, focusing specifically on questions 3, 4, and 5.
So, here's our game plan. We'll kick things off with the core formula, the engine behind this whole technique. Then, we're going to ramp it up with integrals that you have to solve twice. From there, we'll see how this abstract tool actually helps us find real, tangible areas and volumes. And to wrap it all up, we'll put our new skills to the test with some classic exam-style questions.
First things first. Before we can start running, we've got to learn to walk. So let's get a solid grip on the essential formula and see exactly how it works with a nice foundational example. And here it is. This is the machine that drives everything we're doing today. The whole point of this formula is to let us swap out a difficult, sometimes even impossible integral for one that's way, way simpler. The real art here, the whole strategy, is in how you choose your u and your dv.
Okay, let's put this thing to work with a classic problem. This example is honestly the perfect way to see the core mechanics of this whole process in action.
The secret is just being methodical. We pick u to be x for one simple reason. Its derivative is just 1. And that's going to simplify our problem. That leaves dv as e to the x dx, which, thankfully, is super easy to integrate. Now look at the result. Our new integral on the right is just the integral of e to the x. That huge simplification is like a green light. It tells you that you absolutely made the right choice.
All right, time to level up. What happens when applying the formula just once isn't enough? We're about to dive into problems where you have to go through the whole process, not once, but twice. This is question 3c from the exercise. And the big flashing clue here is that x squared term. See, when you differentiate x squared once, you get 2x. That's simpler, sure, but you still got an x hanging around. That's your signal that one round of integration by parts just isn't going to cut it.
Our strategy is exactly the same though. We're going to target that polynomial term, x squared, and set it as our u, because its derivative, 2x, is a clear step down in complexity. This leaves dv as sin x dx, which integrates nice and cleanly to negative cos x.
So, after applying the formula the first time, this is what we've got. Hey, we've made progress. The x squared has become just an x. But we're not home free yet. We're left with another integral, the integral of x cos x, and that little guy still needs integration by parts. So, we go again. We apply the exact same logic to this new, simpler integral. We choose u as x because its derivative is just 1, a constant. And that is the key move that will finally get rid of the x term, leaving us with an integral we can solve straight up. After we do that second integration, substitute everything back in, and carefully calculate the values at our limits of 0 and pi, we finally land on our exact answer, pi squared minus 4.
Okay, so we can solve these complicated integrals. But so what? What's the point? Well, now we get to see why this is so incredibly useful. We can use this exact technique to find the precise area under curves that we'd have no other way to measure.
And this, right here, is a brilliant illustration of what we're actually doing. I mean, look at these shapes. We're not just crunching abstract numbers. These numbers represent a real physical space trapped between that curve and the x-axis. And integration gives us the power to measure that space perfectly. This one corresponds to graph B from the textbook, which is question 4b. To find that shaded area, we need to set up and evaluate a definite integral, the integral from 0 to pi of x times sin x dx.
Now the setup here is identical to what we've been doing. We're still picking u to knock down that polynomial. The only new wrinkle is that this is a definite integral. We're not just looking for a general formula anymore, we're calculating a specific number, an area, between 0 and pi.
Once we have our integral solved, it's time to apply those limits. The process is pretty straightforward. First, we plug in the upper limit, pi, into the entire expression. Then, we do the exact same thing for the lower limit, 0. The final area is just the difference between those two results.
And would you look at that? The exact area under that beautiful curve, from 0 to pi, is simply pi. It's just such a clean, elegant result.
Let's take this one incredible step further. We just found a 2D area, but what if we take that flat area and rotate it, spin it all the way around the x-axis? We create a 3D solid, and guess what? We can calculate its exact volume.
To find the volume of that solid, we use this awesome formula for the volume of revolution. You can think of it as integrating a whole stack of infinitely thin circular disks. The key thing to remember is that we integrate pi times the function squared.
So for question 5, we're given this function. The very first step is to square it, which gives us y squared equals e to the minus 2x times the quantity x plus 2. Now we take this expression and plug it right into our volume formula, which gives us an integral we can actually solve. This integral looks pretty intimidating, I know, but we can break it down into two parts that are much easier to handle. The key is recognizing that the first part, the integral of x times e to the minus 2x, is a standard integration by parts problem, just like the ones we've already done. In fact, many textbooks just list the results for these common forms. In this case, that integral works out to be 1/4. The second part is just a simple exponential integral, which comes out to 1. Then we just add those results together.
So the final volume of that really complex-looking solid is exactly 5 pi over 4. We've literally gone from a formula on a page to a tangible 3D volume, all thanks to integration. It's amazing.
All right, you've built up the skills. You've gone from single applications to doubles, from abstract math to calculating real areas and volumes. So now, let's put it all together and really sharpen those skills by tackling a couple of questions you'd likely see on an exam.
Here's a super common one, and the whole trick to this problem is making the right choice for you. Just think about it for a second. We don't have a simple, straightforward rule for integrating the natural log of x. That's a huge hint. It basically forces our hand. We have to choose ln of x as our u so we can differentiate it instead of integrating it.
And that one single strategic choice completely unlocks the problem. Differentiating ln x gives us the simple 1 over x, and integrating x dx is a piece of cake. When we plug all that into the formula, the new integral becomes incredibly easy to solve, and it leads us straight to the final answer.
Now this is a really fascinating case. Think about it. Neither e to the x nor cosine x really gets any simpler when you differentiate or integrate them. They just kind of cycle back and forth. That's our clue that we'll have to integrate by parts twice, and when we do, something really clever is going to happen. And this is where it gets really cool. After we apply integration by parts a second time, something amazing happens. Notice how the original integral we started with has just popped up again on the right-hand side of the equation. Now, it looks like we're just stuck in a loop, right? But that loop is actually the key to solving the whole thing. So how do we break out of the loop? We use a brilliant little algebra trick. Let's just call our original integral I for short. Now our equation looks like this. I equals some function minus I. Suddenly, it's not a calculus problem anymore. It's a simple algebra problem. We just add I to both sides, get 2I, and then divide by 2 to solve for our original integral. It's just a beautiful way to sidestep what looks like an infinite loop. So, the crucial thing to take away here is that integration by parts isn't some kind of magic. It's a system. It's a process for turning integrals you can't solve into ones you can. And the key is just practice. As you finish up here, think about this. Which part of that process trips you up the most? Is it picking the u and dv? Is it the algebra in the middle? Or is it dealing with the limits at the end? Pinpointing that specific step is your next challenge on the road to mastering this.